Actually, in the initial invitation, I mean both the Purushottam and Pinaki, they said that you just come. You participate in the meeting, but you don't have to talk. And then finally, they said that Shomu cannot come because he is actually reaching within next 2 days or so. Or anyway, anyway, he cannot. He could not present his things here. So, I will try to present, and of course, there is some change in the title, because the main thing that he wanted to kind of discuss is not yet published or not yet and is quite technical. So, that part will be very shortened, and I do not really know, and whatever I know I cannot tell, because they have not yet published it. So, I will present essentially some general stuff and then introduce what they did. Quite an interesting study. Now, it has been discussed in many ways that if you have a fracture, the force versus displacement or kind of emissions, energy emissions are kind of in steps. There are various discrete values it can, and he gave one result from a lab quake, ultrasonic emissions. He, together with his colleagues, is collecting some Indian plate data for the Richter magnitude and the quake time series, and then for some plates, I believe he told me, and I do not see the plates that he have considered, but anyway, they are doing it. Of course, you get this kind of time series, which is very simple, that the energy released in the quake and the probability of that energy, and the energy will go kind of a log plot will give you a power law, and that is the famous Gutenberg-Richter law. So, this is also collected by Peerbuck sometime and collaborators sometime back. Now, this is all these are actually talking about that the energy release has a kind of power law tail, which comes essentially from the original observation of Gutenberg and Richter, that the number of quakes with of Richter magnitude m or more actually goes down with the, which is of course this is the relation. Now, this magnitude and energy is probably energy goes as goes exponentially with them. Some of the nuclear explosions, underground explosions created the seismic waves, and sometimes this is seen that the magnitude energy is kind of exponential in m with some constant. So, basically beta is related to log of, so m is log e. So, that gives this kind of relation, and beta comes from this b and the energy relation constant, this in the exponent. But we will confine to this law, and this has been seen in many ways, and then I will actually skip this at this moment, and I will come back. And this is of course, Shomo is, I believe it is part of his job talks. So he actually tried to mention that he had this review of modern physics, then this book together with Purushottam and others, and then this volume from the Proceedings of Royal Society. It's philosophical transactions, where some of these kind of experts, many of the experts in fracture and earthquake kind of discussed latest researches. So, and he is the lead editor of that. Now, we can go back to the statistics that we were showing. This is the kind of statistics you get this Gutenberg-Richter law, and this power law is there. But earlier also there were some observations, but this is a nice paper, I mean in geophysical research, and it gave many things. One important thing is, even for a kind of simple setup where I mean I think the pressure sensors are on across this, and something is pushed from within the cylinder, with some grains you are pushing this. You can get the pressure fluctuations. I mean it's essentially looks like the stresses eventually have some major fall, and on a long time scale you will see something like this. It is almost periodic, but not quite, and within that there are, within two big falls, there are some responses. One can see that there is a characteristic difference far away, I mean after a big shock, big fall in the stress, the kind of fluctuations are like this, and qualitatively you can see there are short range correlations here, there are long range correlations here. So, they are growing as you are approaching this. So, the statistics, of course, when Gutenberg Richter B exponent probably changes its character. Now, that was, there were many other previous observations. One nice thing was by the Japanese group, I mean University of Tokyo Earth Science department, Kawamura and Hatano from there, Kato is also from there, and of course we were there, but it is actually their study. They actually collected all the JUNEC data for I mean earthquakes in various epicenters across Japan during 85 to 98, and what they observed is that if you average over, I mean the kind of event frequency versus Richter magnitude, somehow this is now small m. Of course, the total thing is showing a very steady power law. But then if you collect only those data, seismic data for any of the earthquake, major fault, major quake, and for the 100 days before the quake, and also within a radius of the epicenter 30 kilometers within the epicenter, of course minimum magnitude has to be there. Then you collect them, then you clearly see a lower slope. Now, this is I mean I would say that this is something that, I mean this slope merged with this will give you a bigger one, but if you do it here you will get a lower slope, and that is actually observed. There were earlier observations, even earlier, that it's cliff failure. I mean from various, I mean I think there were some I mean sensors given some cliff failure, you can again find out the energy versus number of quakes and so on, number of failures, avalanches, and you can see that the effective B value, the exponent B that we were talking in Gutenberg Richter law, is actually not a constant. Just before the major failure there is a dip, as in the previous slide we showed that these are actually very near the quake epicenter, and also for very I mean late, I mean just before the failure you have a lower slope. So, there were indications that this correlation, if one could find out, probably one could get, because this statistics is not going to help, because you are only getting the statistics after everything is done. I mean you have nothing, I mean you can kind of anticipate that it looks like it is this, and we do not know the real slope and so on. So, the real question is, I mean okay, and one good thing was done, and it is still not published, Shomo and Lucas Goering, and they collected the data from US of the power blackouts. I mean you know that, I mean these various grids are distributing power, and if I mean and each has some kind of threshold, and if the power consumption actually grows, then some of the local failures occur, then of course the others give the supply and so on. So, you can see that effectively, I mean from the slope of this, I mean outage versus its size, you can get the exponents, and you can see that when the load is high, the effective B exponent is actually going down. This is the kind of slope of this curves. So, this slope is anti-correlated with the load demand. I mean, whenever there is a dip in the increase in the load, then there is a dip. Whenever there is a decrease in the load, there is an increase in the slope. They are trying to publish this. This is again an interesting thing that it's happening in all the kind of coupled dynamical networks. Yes.
This is data experimental.
Yeah. This is taken from US powers.
From theory, if you take
No, there is no theory.
I'm saying that theory, the load has to be increased in such a way that the system goes through such a metastable steps. So, if you
Yeah.
you are saying load is increased,
Continuous load. No. During the say, I think this is one is during the month of the year, and this is the time of the day. Now, probably in the evening, you or I don't know. No, it is the time of the day is during summer time, mid noon, you have the maximum load, and then effective. From the avalanche, the tripping of the power grids, you get the exponent, and you can see that it is lower. Now, if you do it for the whole year, again I think in summer time you have a maximum load demand, and you have a effective avalanche exponent is lower. So, this is actually an important, this entirely is an observation, that the thing is if you take the power outage as the earthquakes, and you try to find out the Gutenberg-Richter exponent, the B value, then like in earthquakes, but here it is I think more prominent, that they find that this B exponent value is essentially the Gutenberg-Richter exponent has an anti-correlation with the load demand. And this is important. So that is exactly what we we were saying, that this Japanese analysis, this JUNEC data is very reliable data, and it clearly shows that just near the epicenters, and also for not for all period, but just take the period before the major quake, you have the Gutenberg-Richter exponent lower. So, sorry. And this is also, you can find out, the map, near the, Malaysian, you can find out the B value, and the B value of this Gutenberg-Richter B value, and you can see where it is lower and where there is a chance that there would be major quake, and so that is the kind of thing this was given. Now, so this is statistical thing, but it is not helping. There was a nice again, as I said, it is Shoumo's slides. Shoumo says that there was an event, that in your in this town in 2009 there were some deadly earthquake, and there was a deadly earthquake, and some 300 people died. But there were going some precursors where people could feel, because there were some pre-shocks were there, but some of the scientists kind of held a meeting, and then they said that, well, this is not sufficient evidence that there would be a shock, but major shock, but it did happen. And after the earthquake, the court, local court actually convicted all the scientists, 6 scientists who took a public stance that there is no major indication. So, and in fact they had to be acquitted quite some time later, I think 4 or 5 years after that. So, the question is these statistics are not actually credible enough. I mean, sometimes, I mean, you can get the exponents which kind of indicates that's not going to work, and sometimes. So this is not science yet. Now, well, I mean, this part, I do not know what exactly they did. I can tell you what we were trying. That was very simple, and this didn't work. Of course, this is not supposed to work, but we tried. I mean, but they are doing now much better, and we know now. So what we were doing is we assumed that I think well, some kind of neural, I mean, is a kind of back propagation algorithm. I mean, you take. So this is the input layer. This is you have to add a hidden layer, and then perhaps an output. And each of these variables, neurons, has a kind of SI, and you have a state is between 1 to -1, and so on. And SI at time t plus 1, I mean, and there are interactions and so you take say this is the output layer and this is the input layer. So output layer, for example, its time t plus 1, its state will be given by tan hyperbolic of these interactions are called Jij. Jij from one layer to the next layer. So Jij, Sj, and time t, earlier time, and I mean, so you can make it kind of a threshold one. And so what we were trying was without much hope, of course, because we cannot have a big input layer. So the time series that we were showing, any time series of for example, this time, I mean, this kind of time series. So you take the last, I mean, you give a training period of up to a few 3 or 4. I mean, there are many time, I mean, data. You give 3 of them, values between 0 to 1, you normalize these values to 0 to 1, you give them at the input, that determines this layer's things. So, yeah, input is, say, I mean, I am giving S at time t, S of this, S of 3 input layer, S of 2 input layer, and I give time, and S of input layer, but 1. So this is the thing, and I give the value, say, time at time t equal to say 30, at time t equal to 31, at time t equal to 32. I give this, and then I ask at the output what would be, what this network is saying about 33, S output at time 33. I give this input and I ask what would be S of 33. Now these Jijs are of course not all ferro type, I mean all not positive. They have to be, I mean otherwise you cannot accommodate this. Now and then you find that this output, I mean you also know this S of 33. So you go back propagate, modify these two as far as possible, and then you find that it's not improving very much. Then you take the error further down and then modify that and then say that this is the best that we can do. And then you change for the next, I mean, so this one is say 31, 32, 33, I have now, and then I ask for 34. This way, after some time, you expect that it will be able to tell you something about this time series. Yes?
But the signal at the input is what? The amplitude?
The amplitude, yeah. The amplitude at any time. So there are time series. This is the time series actually. So these are that are given, and I make it between 0 to 1. I mean, you divide by the maximum amplitude, and then between -1 to +1, and then I just make it, and so Jij's can be negative, and so it can be between plus and -1, and so you can do that. But you see, I mean, the problem is to manage with so many Jij's as your network size increases. Very soon you do not get anything, and so you get frustrated, and it does not work that way. Yeah, yeah. Oh, okay, okay. The idea is that this kind of fluctuations, when I am here, somehow the network will learn that this will be another this kind of fluctuation. You give 3 of these and then ask for the next one, it will be of this kind of fluctuation. But when you give these 3, it will give a complete different series. Tell me that, I mean, this is kind of lumping and more short range correlations are coming. If that would be, then I would be able to tell, yeah, now my network is actually giving some idea of this thing.
But when you actually do it, how many nodes are there? Just 3?
Oh, no, this is for simplicity only, because it is difficult to manage. I mean, of course, the simplest thing is 1 and 1 interaction. Of course, it will not give you anything, either positive interaction or so 1 input, 1 output. That will not work. Now then you want, say, 2 inputs and 1 output. You try, you will not get much, because there are 2 interactions, and you can make positive, negative, everything, but you cannot. Yeah, that's the thing. I mean, then very soon you are, I mean, limited by your ability to manage how many variables I will be able to manage properly, so that I can get a proper thing. Actually, this paper reported, this was reported in 2017, and I did not notice it. I mean, they did a very nice thing. Yes. Huh.
So basically, for this kind of measurements, where we are actually predicting an output at the next later instant. So what is
Not predicting, we are trying. Yeah.
So this is based on the fundamental supervision principles. For example, from the information of the distribution system P, we are actually trying to predict the distribution of some P of T prime based on the earlier information.
Yeah. Yeah.
So for this kind of, so similar kind of things are there in quantum measurement testings, and similar kind of algorithms are already there. But for this kind of prediction, what is fundamental is the infinite order information of this particular coordinate distribution. But this particular paper have actually used the formally first 2-3 order numbers, so variates and all this.
No, the thing is, as I told, it is not really infinite order informations required.
Then it would be more efficient.
Yes and no, but the thing is, okay, no, not this one. Oh, I think I did. So you see, these kind of things were being observed. That, I mean, okay, this in the Gutenberg. Okay, so let us go back. I think this was for. Okay, Gutenberg Richter said that number of quakes of magnitude m will go down this way, this b. Forget about energy and how to connect. I mean, whether m is connected, because that involves another. I mean, the magnitude and the energy released is related exponentially, and there is another factor, and these two will give the beta. So measurement of beta is not very helpful. Measurement of b was already clearly showing, because it is only one parameter now, that was clearly showing that there would be I mean, I think yesterday Sutoshi was also mentioning, you were also mentioning, and so on. So b was already identified that it clearly there is a change in statistics, and that this experiment was clearly showing that there is a change in statistics. I mean, you have to identify that from here you are going to a phase where it is this happening. If you can do that, and if you can capture that, you don't have to really be a infinite network thing. It is a finite system thing, but we were not able to do that. Now, and this was another very nice thing by Shomo and his colleague. They found that the US, I mean this power network tripping has a clear indication that this B magnitude has an anti-correlation with the load demand, whether it is during the day or throughout the year. If you make the average, the load peaks in the summer time, and then the effective Gutenberg-Richter exponent is much smaller. Similarly, during the day, perhaps summertime, you see that near the noon, the load demand is getting higher and you have the effective B exponent higher. If there is a tripping mechanism in your supply thing, then there are small avalanches. I mean, the thing is, from that avalanche you can get these things. This is beautiful. I mean, this actually shows that this thing is there in the correlations. You have to find that out. And this correlation doesn't really require an infinite knowledge. It really requires a very simple detection that there is a change. Now, this was not, we were not able, and what they did, and as you can see that, I mean, if we are just dependent on the statistics, we may have to be end up in jail. And now these people are saying, now this I cannot tell, I mean, they have gone to 2,500, I mean 250,000 total events as the information, and they could predict the next 25,000. Now, for this, what they did is, they didn't really go to the earthquake data. This is another thing. The real earthquakes have the problem that the shocks that you are seeing, whether it is an aftershock effect of a previous thing or the pre-shocks of this thing, is very difficult. So, the lab quakes are very important, very nice here. I missed your talk, but I mean, I am sure, I mean, people know it. The lab quakes are a fantastic thing. Another thing is, of course, that is also what we were trying, is a very simple model which, sorry, let me go back, because that is the only thing I can talk a little more. Of course, that is not very interesting. This is the thing. Now, this was again Shomo, Purushottam. There is a mistake. Sorry, this is not mine. Shomo didn't put your name. Sorry, this is Shomo, Purushottam and myself. No. But this is, you see, this model is simple. I mean, what my intention is that what they are now checking is some of these, instead of lab quakes, they are actually taking this theoretical model of kind of Parizhnopev model or numerical version of the Parizhnopev model or Langer's kind of version originally, but it is now much more simpler and is in the university class of Edwards Wilkinson. Now it is demonstrated clearly, and the idea is like this. The original Parizhnopev model was for the earthquake, which any earth science textbook will show, that you take a rough table, there are some wooden blocks, there are hook springs, each of them are connected. It is a chain. You have a train, and this train is on, so there are blocks on this rough table connected by springs. There is a motor, uniformly you are pulling that thing. It is an inverse thing, that instead of the tectonic plate moving, here it is the continent is moving, but it is the same thing. Now, what happens is that the blocks try to, because of their weight and the friction between the surfaces, they will actually try to stick. Then occasionally there will be one or two will fail, because the friction force is not uniform, has randomness because of non-linearity, velocity dependent non-linearity and so on. So, creep will be non-uniform and there will be some failure, and then the springs will have, I mean, from measuring, I mean, taking photographs of different time, you will find that essentially there would be the time series of the energy, the stored energy in the chain would be like this, I mean, this time, and from the blocks, I mean, positions, I mean, you can measure the positions at different times of these blocks, and from that you can find out that since spring constant is the same, from the distance square you can find out the energy. So, this is the elastic energy stored in the system as the springs either compress or I mean, this is on the rough table, and you are pulling by a motor. Now, from this you will see that, I mean, it will grow, there will be small failures, and then, so this is the charging time, and after this, I mean, it will be doing like this. So, this is the kind of critical state that you have reached. So, this charging time and so on. Now, this was actually being tried to model like this, that you take the blocks and they are actually replaced by, I mean, this is the original Boris-Nopov model, which is an experimental model. You take in this paper, you take the contacts only on discrete lattices. Now, this lattice might have, I mean, for example, there might be no support here, one missing or two missing, something like this. The spring is uniform thing. So, it has a discrete possibilities, and thus, I mean, it is a harmonic springs, I mean, there. So, you can always find out, and so when you are pulling this train of these blocks, and these are rigid, and the interactions, I mean, the friction interaction is here. You just assume that these frictions are actually like threshold type, there is some value which is uniformly distributed. Take a distribution. So, anyway, now once you make it a threshold type system, you can immediately, and it is actually very much equivalent to Edwards-Wilkinson model, but done in a different way. I do not want to. So, then you could check that all the exponents, I mean, first of all, nobody, I mean, here what is the force required to make it, I mean, make the interface moving and find the velocity of the interface exponent, so on. That is not, nobody actually tries to find in the earthquake, because that happened long, I mean, after we see the system, because it is already there. So, you can do that kind of thing, you will get the same exponent value here in the same model. I mean, in this Boris-Nopov version of the model, I mean, or a kind of discretized version of the Boris-Nopov, you can get the same exponents. On the other hand, nobody tried to find out in the Edwards-Wilkinson model the Gutenberg-Richter exponent, and it turns out it is the same class as Boris-Nopov one. Anyway, so these things were shown, and this system was so simple to develop, I mean, simulate in the computer, one could do a lot, and they actually now take that to predict, and actually they now take, I mean, the average, I mean, okay, they try to learn several things. These inputs are no longer the time series, the average magnitude, average correlation, the correlation, and these are the things they want to, the network wants to learn, and time correlations and so on. But anyway, there were few things which are not exactly the time series itself. That was the great change when that paper in I showed indicated that this is the better way, and with that you can see what is the result they are getting. Apparently very simple, the time before failure, any time this is I mean, real event. So, real event, forget it at this moment, this is the prediction. Now, at any time it says, say 250, after 250, this is the time before, I mean, to the next failure. So, it says now after 250 units of time there would be a failure, but you see that, I mean, it is much, maybe less, but sometimes it says 250, okay, you can see that this is the real data, it is here. But as one, I mean, this is after a major shock. Now, this you can see that now this data, and as this slope is coming close to the observation, because this is the real time, I mean required. I mean this is this pink one is the real time before until the next shock will come. I mean, so this was something like 300 something. And the real prediction from this after learning the series is somewhere here. It is saying something smaller, but then gradually just before this, I mean it is falling more and more on this line, and perhaps about 20 time units earlier it is almost saying that this will be the time. So, I mean what I am saying is, okay, so this is the thing. I mean you have a major quake here, I mean, and that is happening after some 320 say time. It says no, it will be, I mean the prediction is at this stage when you are here, there will be a prediction that after 250 or 260 time steps that would be. You are already wrong, but then follow this, it will give another value later on, give you another value. Almost at about 100, it is almost saying what it should have been 100, but it is not quite. By 30 or so, it has already fallen on the line, and it is saying 30 time unit later you will have a failure, and it is indeed happening. So, long before the quake, it was making some mistake, but it is adjusting, and then you can see that here, for example, the real quake is probably happening after this. Real quake is happening somewhere here 200. It is saying 250 times later. But you follow the thing, after something like 100 time units, it has already saying what the time will be. You are actually following this line. So, this is quite an achievement. I mean somehow they have done it, and they are actually preparing the manuscript. So, until that they will not give the details, and so I do not know, but this is a kind of major thing, because statistics we could see that there is a clear change in the statistics, and it is very, very important. I mean it is kind of $1 million thing if you could actually appreciate what is the change in the statistics where. So far none of this, and there is another thing, of course, if you could do it for stock market, that is another major thing. But the thing is, stock market has a different problem. It is even more, because earth will never change its dynamics knowing that now you are able to predict. But if it is known that this stock will fail, and if it is dependable enough, then people will make the market different. So, the expectation will, so that has to be a second grade, I mean higher order problem. But the thing is, these kind of things are still so simple, yet we cannot. Since that, for example, earthquake is a much smaller system than an infinite critical system that we think, yet we cannot do anything so far. But now it looks like very simple algorithms are getting available. I mean, I think, I mean there he has not given, or maybe he has given. No, he has not given. There is actually a site, either Brookhaven National Lab or somebody has now declared just for high school students to write programs. You know that, I mean who Brookhaven or competition, just for school children, that can you give better things. I will give you the laboratory quake data. You do not have to really go to the real data. Give me an algorithm for which your prediction will be, this kind of prediction will be better than what we have. And they are expecting that it does not require any major scientist. It can be done by young people, and if they can do, there is some prize, of course. I mean, and of course they will get the names added. This program will have also the name added to that. So, I would think that many of our students should try, whether maybe the date is very near, so that is not possible, but we should try to get the time series kind of prediction with some kind of neural network, and because these correlations are almost there, people have understood, I mean and observed over many years now, and it looks like it is a very generic feature that very, I mean short range correlations start appearing and then it fails, and this can be captured by some neural network models, artificial models. So, there are even, so I think this is a great achievement, and by the way there are now in nature earth science, nature earth science or nature earth science, at least I have seen 5 or 6 papers, they have done independent different algorithms, they all predict, but then you cannot get those programs, because that is the, but they are saying that this is what we can do. And each of them is now almost within a year or two, everyone is going beyond others. And it looks like now it is a matter of a few years, we will have very dependable algorithm. But if not, I mean we should have a large attempt now. Later on, no problem, no real gain, because they will sell us, we will buy that program, and we will do something for our epicenters. And we have some, I mean you know, the most, one of the most active I mean earth science wise continent is India. I mean we are still kind of encroaching within China's belly. Every year about a 1 inch or so we are penetrating. That is not the reason we have some problem with China, but I mean we are still very active. Himalaya is still in, I mean it is pushing, the continent is pushing, and Himalaya is still active, growing. So, we need desperately our computer scientists, our young thing, how much we can predict, and this will help eventually many other places, but this is one very important one for us, and it looks like very active time now. And there are so many papers coming. I could give the reference, somehow he has not given here. So, I think Nature, this earth science one, I mean Nature has at least 6 papers, each of them are using neural networks to predict better and better. And the competition is also from some of the labs. We should have also our institutes also, I mean computer science departments to initiate some such in competitions among the school children to try their, because this is nothing, you develop algorithms to generate this, and already some things are clear, some things are generally available. It is not that, I mean nothing is available. The major breakthrough is already there, at least one major breakthrough. I do not know whether it will be the final one. Okay, thank you very much.